Hello everyone, and welcome to this STM32Trust video series on the secure firmware install solution by ST. My name is Maurizio Gentili, Security Application Engineer with ST in the Microcontroller division, and I will guide you through the details of the SFI solution for secure manufacturing. Here is the agenda for this video. We will start with an introduction of the problem solved by the secure firmware install solution, followed by an overview of the tools needed for SFI and a high-level description of the flow. We will then discuss some details and specificities of the implementation for each STM32 family. And finally, we will share some of the resources that you can refer to for your evaluations and developments with SFI. But let's start first with an introduction. The problems that SFI targets are mainly two: how to protect the OEM application firmware at contract manufacturer when devices are programmed for the first time, and how to avoid overproduction. The graph shows a typical manufacturing process, where an OEM develops a firmware and needs this firmware to be flashed to the STM32 during manufacturing. The manufacturing process is responsibility of the contract manufacturer that purchases the STM32 virgin parts from ST through either sales or distribution channels. In this typical scenario, the OEM sends the firmware to the contract manufacturer in clear. The application code is then potentially exposed to attacks. The OEM must trust the CM, hoping that its application code is not stolen or tampered with, and that the CM does not overproduce parts. The Secure Firmware Install SFI is a new security solution introduced by ST to address this problem and to enable secure manufacturing in an untrusted manufacturing environment. As we will describe in the next sections, the solution guarantees authenticity, integrity, and confidentiality of the OEM firmware. It ensures that only genuine STM32 microcontrollers are programmed with the OEM firmware and allows to count the number of STM32 parts that are manufactured and programmed with the OEM code. The SFI process is compatible with STM32 parts provided with RSS or Root Security Services. RSS is a security expansion of the STM32 system bootloader and, as we will see in more details in the next sections, is responsible for the SFI steps that happen at the device side. RSS embeds a unique asymmetric ECC private key together with a corresponding certificate for device authentication. In addition, it makes use of the STM32 security features, such for example the readout protection, to prevent the OEM code from being accessed by the CM or being extracted or disclosed. As depicted here, SFI is supported by STM32L5, STM32WL, and STM32H7, that are provided with the RSS extension of the system bootloader in ROM code. In addition, a specific part number of the STM32L4 family, STM32L462CE, compatible with SFI is available. As it will be presented later, the SFI solution for the STM32L462CE is slightly different from the others. Instead of being an extension of the system bootloader in ROM code, in this case, a custom implementation of a secure bootloader offering the RSS services is provisioning the user flash of the micro. Additional details will be provided in a section dedicated to the STM32 implementation, together with some pointers to the documentation, where you can find all the information for each family. In an SFI-enabled manufacturing, the OEM creates and manages his own secret firmware encryption key that is used to encrypt his application code in the form of an SFI package. Then, he securely transfers the key to the CM that will use it for decryption of the package during manufacturing. ST produces secure RSS-enabled STM32, provisioned with a unique private key and certificate, that will be available for purchase by the CM through regular sales and distribution channels. The CM will then be able to securely install the OEM application code using secure manufacturing SFI tools. Let's now review the list of tools that are part of the SFI ecosystem and enable the solution. As shown in the previous slides, the SFI process guarantees a secure way for the OEM to deliver to the CM the key used to encrypt the application code. In order to secure this transfer, ST introduced the STM32HSM, a hardware security module used to secure the programming of STM32 SFI-enabled devices and avoid product counterfeiting at contract manufacturers' premises. The OEM key is securely stored in the HSM smart card that guarantees the same level of protection of a credit card. Main features of STM32HSM are secure storage of the OEM firmware encryption key and the license counter for SFI operations, the identification of the genuine firmware and STM32 products, and a token generation in a smart card format. STM32 HSM is supported by STM32 Programmer and an STM32 Trusted Package Creator. You can find all the information about the latest version of STM32 HSM, currently v2, on st.com. Looking for STM32 HSM on the search bar and clicking on the link, you will be redirected to this landing page, where you can find an overview of the product and all its features. Then, for additional details, you can switch to the Documentation tab and open the corresponding data brief. The other tools that are part of the SFI ecosystem are the STM32 Programmer and STM32 Trusted Package Creator. STM32 Programmer is a software tool for programming STM32 devices that supports all STM32, and it is compatible with Windows, Mac, and Linux environment. The tool is also compatible with the STM32 HSM module presented before. During the installation of STM32 Programmer, you have the option to add an additional software, STM32 Trusted Package Creator, that actually enables the SFI process. STM32 Trusted Package Creator comes with both a graphical user interface and a command line interface, and can be used to generate the SFI files and to provision the HSM module. Also in this case, all the information about STM32 Programmer and of its add-in module STM32 Trusted Package Creator are available on st.com. Looking for STM32 Programmer in the search bar and clicking on the link, you will be redirected to this landing page, where you can find a product overview, all the features, and download the software, depending on your operating system. Also in this case, going back to the Documentation tab, you will have access to user manuals and application notes that could be very useful during your developments. Now that we introduced the tools enabling SFI, we can get a closer look to the whole process. This overview is covered in Application Note 4992. You can refer to the related sections for additional details. The graph shows the steps the SFI process goes through to secure the manufacturing. The first phase happens at the OEM, that is responsible for firmware development, for creating and managing the secret keys used to protect the transport of the firmware image, and for the creation of the SFI package. In step 1, the OEM creates an AES secret key, and it is responsible to keep it secret, and uses STM32 Trusted Package Creator to create the encrypted SFI image that includes the original firmware and the option bytes configuration of the device after the SFI process. In step 2, the OEM programs the STM32 HSM with the AES secret key used in step 1 for encrypting the SFI image, and initialize it with a counter that will limit the number of STM32 devices that could be programmed with this card. The second phase of the process takes place at the contract manufacturer, CM, that receives from the OEM the encrypted SFI package and the HSM card, and it is responsible for installing the STM32 firmware to the device. In step 3, the STM32 Programmer initiates the SFI process. In step 4, it asks the STM32 for its unique certificate. In step 5, the device certificate is checked to make sure the STM32 is authentic. After verifying the device authenticity in step 6, the HSM provides a license, a unique per device cryptographic package, including the AES secret key. At this step, the counter of the HSM is decremented so as to avoid overproduction. The STM32 can then retrieve the AES secret key and proceeds in step 8 with the firmware installation and option bytes programming. As we will describe in more details in the following section, the implementation of the STM32 Secure Bootloader used in SFI configures the onboard STM32 security features to protect access to the user flash memory or the SRAM, and therefore preventing the OEM code from being extracted or disclosed during the whole process. An additional feature available for selected STM32 microcontrollers is the support for external flash programming, named SFI-X. SFI-X is based on the on-the-fly decryption peripheral, designed to protect confidentiality of data and code in external memories. The content is stored encrypted in the external memory, and the on-the-fly DAC allows for an on-the-fly decryption using a dedicated key. In the SFI-X scenario, together with programming the internal memory as described before, the SFI process can be used to securely flash the content of the external memory, and at the same time to protect the provisioning of the key needed for decrypting it. The key could be either part of the internal firmware image, or it can be randomly generated. Also in this case, you can refer to the application note 4992 for additional details. The document includes a section dedicated to the SFIX process and all the possible configuration options. Let's now have a look at how STM32 enables Sfi. As mentioned already, the Sfi process is based on the execution of a security-enhanced system bootloader implemented in STM32 that makes use of the available security features, for example RDP, to prevent access and disclosure to the OEM code. In this section, we will highlight some details of this implementation for each STM32 that supports Sfi. The first family of microcontrollers we will review is the STM32H7. In this configuration, the system bootloader is expanded with the RSS services needed to perform Sfi. As depicted in the slide, the RSS-enabled secure bootloader is stored in the internal boot ROM. So the whole STM32 flash is therefore available for the OEM application code, and the part is delivered in RDP level 0. The Sfi process on STM32H7 can be performed over SWD and the JTAG interface. Additional interfaces are available through the STM32 system bootloader, in particular in this case USERT, SPI, and USB DFU. The support of these additional interfaces is unique for each device. All the information on STM32 bootloader are available in application note 2606 on st.com. Looking, for example, for the spec of STM32H7, you will find a list of peripherals and GPIOs supported, and all the relevant information. In addition, for selected part numbers, the on-the-fly decryption peripherals is also available, enabling SFIX for external memory provisioning. The implementation for STM32L5 is slightly different. Also in this case, the secure bootloader is an expansion of the system bootloader, but the code is split in two parts. The first part, with the RSS security services, is stored in the system memory boot ROM, while the second one, named RSS extension, is loaded in the SRAM2 by the host via the RSS. This allows for more flexibility to the process. Similarly to the H7, the whole flash is available to the OEM code, and the products are delivered in RDP level 0. As with STM32H7, the Sfi process can be performed via JTAG and SWD, and with additional interfaces offered by the system bootloader, in this case USERT, SPI, I2C, FTCAN, and USB DFU. And finally, the SFIX is enabled by the on-the-fly decryption. One important note: STM32 bootloader makes use of the trust zone to secure the process. This requires the OEM application to be compatible with the trust zone enabled system. In STM32WL, the structure is similar to the one used in the L5, with the bootloader split in a fixed part in ROM and the one loaded in the SRAM by the host. Also in this case, this leaves the whole flash for the OEM code and allows the delivery of the device in RDP level 0. The Sfi process supports JTAG and SWD interface, and additionally through the system bootloader, users, and SPI. STM32L462 implementation is slightly different compared to the ones described so far. The major difference is that in the L4, the Sfi bootloader is stored in the internal user flash and not in the system bootloader section. The code is composed of two parts, both stored in the user flash, a secure boot and a secure bootloader section. This means that not all the STM32 user flash is available for the OEM application code. In fact, after the Sfi process is completed, the Sfi secure bootloader is erased, but the secure boot part of it, around 4K, is preserved. Because of this, the Sfi process on STM32L4 can be executed only once, and the OEM code must take this offset into account. In addition, because the code is stored in user flash, in order to be Sfi ready, the device is delivered by ST in RDP level 1. In this case, because the system is delivered by ST in RDP level 1, JTAG and SWD interfaces are not available. The only available interfaces are USERT and SPI, not provided by the system bootloader, but provided by the secure bootloader executed in user flash. This concludes the overview of the Sfi solution. In this section, we are going to summarize the resources you could use to find all the additional information for your developments. The best entry point to all the material and resources is the STM32Trust landing page, that includes a section dedicated to SFI, together with links and references for the STM32 security ecosystem from theory to practice MOOCs videos. Another recommendation is to keep the following documents always at hand. The application note 4992 that provides an overview of the SFI solution and process, and where you will find all the information included in this video. The UM2237, that is the generic STM32 programmer reference manual, that includes also a section on the SFI specific commands. The application note 5054, that expands the principle mentioned in the user manual 2237 and is focused on how to use the STM32 programmer in combination to STM32 Trusted Package Creator for SFI. The UM2238 focused on STM32 Trusted Package Creator. And finally, application note 2606, that includes all the details about STM32 system bootloader and related supported interfaces for each microcontroller. Okay, this concludes this first video dedicated to SFI. I'm looking forward to see you for the next chapters of the series, where we will go more in details in the process and demonstrate how to perform secure manufacturing with SFI. Don't forget to visit st.com/STM32Trust for additional information.